Zero human AI collaboration for reliable embedded automotive control systems, reshaping driver assistance through human centered AI integration. Conference 42, DevOps 2026. The speaker introduction Alagar Govindasa, Senior Manager, Electronics R&D, Carbon Products INC. Specialized in embedded automotive control systems and AI integration for safety critical applications, leading research initiatives in human machine collaboration and advanced driver assistance technology. The challenge the limit of traditional automation, rule based systems excel in predictable scenarios but struggle with dynamic real world conditions. Static decision logic cannot adapt to real time perception, prediction, and evolving environmental complexity. Third one, limited context, lack situational awareness and driver state monitoring capabilities. The solution framework, human centered collaborative architecture, AI and human cognition operating as complementary patterns rather than competing entities. One, multisensor perception, camera, radar, and LiDAR fusion for comprehensive environmental awareness. Two, driver state monitoring, gauge tracking, physiological signals, and behavioral analysis. Three, dynamic authority, adaptive allocation between human and AI based on context and readiness. The validation methodology one, simulation testing, controlled virtual environmental testing, thousands of edge cases scenarios and failure modes. Two, controlled experiments, the laboratory settings with the instrumented test tracks measuring precise system responses. Three, naturalistic driving, real world validation across diverse conditions, driver populations, and traffic patterns. Results measurable safety improvements. 1. The critical incident reduction, significant decrease in land departure events across all test conditions, lower collision rates in both simulated and real scenarios, smoother takeover behavior during authority transitions. Human factors, more calibrated driver, trust levels reducing over reliance, improved situational awareness during automated driving, reduced cognitive load during complex driving tasks. Multisensor perception performance. Future architecture significantly outperforms single sensor approaches across environmental conditions. Camera. High resolution visual data for land marking and object classifications. Radar. All weather velocity and distance measurements with penetration capability. LiDAR. Precise 3D spatial mapping for obstacle detection and path planning. The next one is driver state classification accuracy. Advanced monitoring system achieves 90% of accuracy in detecting critical cognitive states. 1. Fatigue detection, gauge pattern, and physiological markers. 2. Distraction recognition, behavioral cues, and attention monitoring. 3. Readiness assessment, real time capability evaluation. The system architecture for model predictive and control integration, the real time performance, multi second scale control loop, execution, maintaining safety critical responsiveness, multi objective optimization, balances competing demands, safety constraints and collision avoidance, passenger comfort and ride quality, energy efficiency and system longevity, regulatory compliance requirements, multimodal feedback architecture, diverse communication channel reduce cognitive load and improve response times during critical transitions. One, the visual displays, heads-up displays and dashboard indicators providing situational context. Auditory alert, the spatial audios, cues and voice notifications for time-critical information. Haptic feedback, steering wheel and seat vibrations for intuitive directional guidance. Dynamic authority allocation. 1. Contact assessment, continuous evaluation of environmental complexity and risk factors. 2. Readiness monitoring, real time driver state analysis and capability determination. 3. Adaptive handoff, seamless authority transfer preserving safety and driver agency. The applications, real world implementation scenarios. 1. Intent aware adaptive cruise control. Predicts driver intentions and adjust following distance based on traffic flow and driver preferences. Cooperative V2V coordination. Vehicle to vehicle communication extends perception range beyond sensor limitations and improves traffic flow efficiency. DevOps integration. The safety critical deployment strategies are three. One, continuous validation pipelines, automated testing frameworks, ensuring regression free updates, and maintaining safety certification requirements. Two, system observability, real time telemetry, anomaly detection, and performance monitoring across distributed fleet deployments. Three, human centered deployment, gradual rollout strategies with the driver feedback loops and adaptive feature enablement based on acceptance pattern. From automation to augmentation, the future of automotive control systems lies not in replacing human drivers, but in merging machine precision with a human intuition to create more adaptive and transparent mobility systems. One, machine precision, millisecond reaction times, 360-degree awareness, consistent performance. Two, human intuition, contextual understanding, ethical decision making, creative problem solving. Thank you.